Hi class, welcome to Unit 4, Lesson 9. We'll be looking at diffraction gratings. So today's learning goal will be to demonstrate an understanding of diffraction gratings and the spectroscope. I know I've achieved these learning goals if I can describe in detail diffraction gratings and the types, diffraction grating and the spectroscope, investigate the difference between double slit and multi-slit interference patterns, and solve problems related to diffraction gratings, as well as applying this thinking and learning to daily problems. A diffraction grating is a device whose surface is ruled with close, equally spaced parallel lines for the purpose of resolving light into spectra. Transmission gratings are transparent, and reflection gratings are mirrored. So this device is used for wave analysis, and with these large parallel slits, they act as individual line sources of light. And so the wave analysis of the pattern produced by these openings resembles the analysis we considered for the double slit experiment. So diffraction grating is a precise array of tiny engraved lines, each of which allows light through. So these grooves, and then they let in light in this way, and the spectrum produced is a mixture of many different wavelengths of light. So the waves passing through the slits interfere constructively on the viewing screen when we have sine theta m equaling m lambda d, where d is the distance between adjacent gratings. So here, the spacing between the gratings. M equals 0, 1, 2, and on is the order of the bright line, or maximum, similar to what we've seen before. This condition for constructive interference is derivable from the path difference, delta L equals d sine theta, between successive pairs of slits in the gratings. And so delta L from the diagram, you can see these segments are the difference in path, or difference in path length. So the difference between double slit and multi-slit scenarios is, since there are more slits in the grating, the multi-source delivers more light energy, yielding a brighter interference pattern. The bright maxima are much sharper and narrower when produced by these diffraction gratings. Since the slits in a diffraction grating are usually closer together, the separation between successive maxima is greater than in a typical double slit setup, and we have increased resolution. As we talked a little bit last time, where we had resolution can be a problem sometimes. And for these reasons, the diffraction grating is a very precise device for measuring the wavelength of light. So there are two common types of diffraction grating: transmission and reflection. To produce a grating of either kind, we need fine lines, and sometimes they're absolutely really fine, to density of, imagine, 10,000 per 1 centimeter on a piece of glass with a diamond tip. So it's extremely, extremely fine. I mean, 10,000 of these per centimeter. And so you can only imagine the precision in these gratings and what they can measure. In a transmission grating, the spaces between the lines transmit the light, and the lines themselves are being opaque. When the line glass is used as a reflection grating type, light falling on it is reflected only in the untouched segments. untouched segments. This reflected light effectively comes from a series of equally spaced sources that provide the diffraction grating interference pattern reflected onto the screen. Line gratings on shiny metal can also be used as a diffraction grating. So let's look at a problem. At what angle will 638 nanometer light produce a second order maximum when passing through a grating of 900 lines per centimeter? So we have a lambda. We also are told second order maximum. So that's m equals 2. When passing through a grating of 900. Now that's not quite d, but we can use it to get d. It's in the same realm. And we were asked to find an angle. So for bright maximum, we said that they constructively interfere and produce maxima using this formula for diffraction gratings. So we put sine theta m equals m lambda d. We have our m, we have our lambda, and we want to find theta, so we can sine inverse. We don't quite have d. We're told it's 900 lines per centimeter is the specifications. So if we want d, we're told how many lines per centimeter. So if we just want to convert a line, so one line we want to convert a line to the unit of centimeters. So we need to multiply this by a conversion factor. And we know to get the units right, we're going to have it line, and we want our desirable unit on top, so the lines will cancel out. And to complete this, we just need to make sure that this conversion factor is equal to 1. And so we're told in the question that the text specifications is 900 lines per centimeter, so we make sure that we keep 900 lines per 1 centimeter. And so since this was told us, and this we know is equal to, there's 900 lines per 1 centimeter, this ratio is equal, or is equal to 1. We multiply like this, and we're left with 1 over 900 centimeters, which works out to be this, and we put it to meters with this value. So that's how we get our d. And now we have everything. So we plug everything in. We declare theta. We specify order 2. So good convention, put 2 for the m. We put substitute 2, 6.38 times 10 to the negative 7 meters, 1.11 times 10 to the negative 5 meters. We have our units matching, meters and meters, and we can just sine inverse this value that comes out, and we find that theta 2 for the second order maxima is 6.60 degrees. That's our final answer. So with different orientations, we have the production of a pattern that is predictable. So for gratings that are at vertical, they produce a horizontal pattern. This is the horizontal pattern. This diagram is showing the patterns, not the gratings. So vertical gratings would be something like this. And for horizontal gratings, the pattern is vertical. So it looks like this. This is our bright central maxima, order 1, order 2, order 3, and so on. for if we cross the gratings, the pattern is also crossed. So if we put the two together, vertical and horizontal gratings, we get this type of pattern. And again, we have a sharp, harsh central maximum, and then you get brightness outward and concentrated a little bit more on these sections, but also radially outward, kind of combining what we see of the two here. And so in actuality, a point source of light is viewed through cross gratings, looks like this. And you can kind of see how these two resemble each other. You have this high ultimate maximum, and we have sharpness here and here, here and here, and along the diagonals. So it produces a really interesting effect. And so you can use this with a spectroscope, which we'll talk about next. So a spectroscope is an instrument that uses diffraction grating to visually observe spectra. If the light striking the grating is not monochromatic but a mixture of wavelengths, each wavelength produces a pattern of bright maxima at different locations on the screen. And so for each of the spectral colors, the maxima occur at different positions, given the effect of a spectrum. So how it works is we have our source of light. It comes in this way. Blast it against the diffraction grating, and it diffracts just like we saw here. It does this, just picture it flipped. And it diffracts it into an observing telescope that's easily observable onto the screen. And since if you use non-monochromatic light, each wavelength, so red and purple and blue, they all have different wavelengths. They're going to produce their own bright maximum at different locations. And so since they're all very different, all the colors, even ones that are close, like yellow, orange, and red, are still very different and apart. And so with our dark spots, we still get our dark spots, but each wavelength, because it's different, shows up its bright maxima for each wavelength at different positions. Notice how none of them are overlapping each other. They're at different positions because the different wavelengths have different maxima. And so they give this effect of a spectrum. And so you can separately study each wavelength and its maxima separately, and you can see the incredible precision that these devices and diffraction gratings produce. That's the end of the lesson for today.